Okay, today I have the pleasure of introducing Dr. Christian Sampson. Christian got his PhD from the University of Utah in 2017, working with Ken Golden. He did a postdoc at UNC Chapel Hill under the mentorship of Chris Jones. And now he's at the Joint Center for Satellite Data Assimilation, which is housed in UCAR. Okay, so today Christian will talk to us about numerical weather prediction, JEDI, and a hybrid tangent linear model.
Oh,
Go
yeah,
ahead,
thank
Christian.
you.
Thank you.
Thanks, Emmanuel. Appreciate it. Thanks for the introduction. Yeah, so today I'll just talk a little bit about what numerical weather prediction is, for those of you that may not know too much about it, what JEDI is, which is maybe people know less about, and then this hybrid tangent linear model, which is an innovation that's recently gone into JEDI, and I think highlights one of the main reasons that JEDI is an important piece of infrastructure to have for numerical weather prediction. So with that, let me just start by introducing the concept of NWP. So the idea is that we have some digital twin of the Earth. We basically grid up the atmosphere. We put all the physical equations, the equations that would govern pressure, temperature, humidity, some physics parameterizations that might handle cloud formation, all into a very complex model at as high a resolution as we can so that we can try to model the Earth. Of course, the models are not perfect, although they are very good. And even a perfect model would be difficult to get an accurate weather prediction with because we need to initialize that model with a state that's as close to the actual Earth state as possible. And of course, we don't know the temperature, pressure, humidity, and everything at every point on the planet and through the atmosphere. So one way we try to get at that information and improve those forecasts is with observations. So this is just a video from NASA showing a bunch of the satellites that are in orbit, constantly taking measurements of the Earth's atmosphere, ocean, land, etc. We also get measurements from airplanes and ships and all over the place. And the combination of these two things is really what makes numerical weather prediction work, at least for, I don't know, we're used to maybe 3 days of accuracy at this point. But we want to keep working and get better and better predictions. So how do we use the data to improve those predictions from the model? That's where the idea of data assimilation comes in. The concept is simple. We basically say we have some model. In this case, this is a governing equation for sea ice, something that I used to work a lot on. This is actually a picture from a model developed by Deborah Sulsky at the University of New Mexico that was directly modeling cracks, one of my favorite sea ice models. But you have some model of some physical process. You have observations of that physical process. So this would be satellite imagery. You can see the cracks in the ice here. And you have a DA scheme that you use to combine these two in some optimal way to get the best estimate of the truth you can. And of course, the better that all three of these things are, the closer this might be to an equal sign, which is what we want. DA can, oh, that's sort of moved out of the way. Oops, let me pull that back so you can see that image. So DA can also be used to fill in gaps. Hopefully you can see that now. This is actually just an image of reanalysis data. So this is a product from ECMWF where they've taken the satellite and data record that we have and combined that with a model to produce a time series of the state of the Earth for this one, I guess looks like a little bit like 40 years or something like that. These are really important tools to have for climate studies. This is a lot of data that you can use to gain insights for reduced order models, try to understand what's going on, look for statistics of trends, etc. But those kinds of reanalysis come from DA products. Okay. So this is, if you want to kind of explore, if you've never really explored some of these products before, I think this is a really great website to do that. This is Windy. It's sort of, I don't know, collates a lot of these different products you can move around the Earth. This one right here is a wind field, but what I kind of like, hopefully you can see down here, there's the ECMWF model, the high resolution rapid refresh model, which is a US product over just the US. There's NOAA GFS you can look at, the ICON model, which I believe is in Germany, high resolution North American, and some more over Canada, et cetera. So you can sort of play with all of these things Look at what the forecasts actually are going to be. There's different products. You can look at precipitation, air pollution, all of these things. This big, massive thing goes into producing these products. It's really interesting. And I'd encourage you to play around with it. It's kind of fun to look at. But that's a place where you could look around if you wanted to. So I just wanted to highlight that.
Christian, is this windy.com? Oh,
Yep.
yes.
Windy.com. Yeah.
Thank you.
Mm-hmm. And yeah, and over on the, let's see, I could show you, well, maybe, let's see, does it want to come back? You can look, there's hurricane warnings, all sorts of interesting things. Oh, I think it's hiding. There we are. I have the video hiding there, but yeah, you can look at temperature, city heat maps, clouds. There's all sorts of stuff, wind, and then at somewhere there's a bar. I can't find it now. You can go up levels in the atmosphere and down, watch the jet stream. It can be a lot of fun. You can spend too much time on it, but I digress. But that's an example of what these NWP systems are producing. They're really important. They're really good for science and, of course, for predicting the weather, especially when we need to know. So let me just give a very quick summary of some data assimilation methods. Typically, the idea is that we have some model. In this case, think of a state X. This would represent like pressure, temperature at every point on the Earth. Might be a big, long vector. You could organize it that way. Advected by some model, so A times X gives us our forecast. Other ingredients that go into this would be this thing called H, which is an observation operator. I'll show a cartoon of that in a minute, but this is an operator that takes your model state to whatever your observation is. So this might be sea ice emissivity to satellite radiances measured at the top of the atmosphere. We have a background error or forecast error covariance. This is an estimate of how wrong our model is. And then we have observation error covariances. This is an estimate of how wrong our observations are. There's going to be issues with both of them. And sometimes they're assumed normally distributed. There's non-Gaussian versions, but for this one, it's nice if we assume things are Gaussian. There's some fun correspondences, but one version is this optimal interpolation, or the Kalman filter, which, as it's often called, where we'd have our forecast, which gets updated. If you notice, this Y here would be our observations. I don't think I listed that anywhere, but Y would be observations of your state. H is taking your forecast to that state. You're looking at the difference, and it's being multiplied, by this Kalman gain here. And then you update that to get what we call the analysis, denoted by the superscript A. So that would be our best guess of the truth. This Kalman gain is a product of these matrices. You can derive this in a number of different ways. There's variational methods. This one is called 3D VAR, where we write down a cost function. We're looking at an inner product with our forecast and our observations. Y, this Y would be like our H of X, F. There's our error covariance matrices. You minimize this thing. And if you minimize this under a Gaussian assumption, you actually just get the Kalman filter. So there's a correspondence there. There's 4D VAR, which is something I'll talk a little bit more about today with this hybrid tangent linear model. This one uses a time series of observations. So here, if you notice, we're summing up over various times. I'll show a cartoon of this, but we still have the same background error covariance, OBS error covariance. We just have to move our model forward in time. Or we could look at this as a Bayesian statistics problem, probability of the state given the observations. If we look at that in terms of Bayesian statistics, assume things are Gaussian and do a maximum likelihood analysis, we actually get back the same thing that 3D VAR gives us if we take derivatives of this cost function or the optimal interpolation. So these three things correspond when things are Gaussian and linear and nice, which is kind of cool. But that's just a quick overview of some of the ways. So you can sort of see what people do. Whoops, there. Oh, my mouse is moving things. Cost functions, statistics, interpolation, all sorts of ideas, but they correspond, but lots of ways to bring data into your forecast. This is just a cartoon of H to have a sense of it. I like sea ice, so this is a fun one for me. You might have, say, melt ponds on top of ice or open water and ice has a specific microwave emissivity, and melt ponds look just like open water really to a satellite, but those will emit microwaves that might get measured at a 20-kilometer resolution by some satellite overhead that just gives a vector of light intensities at different frequencies. Your H, in this case, should map your ice state that your model might have to those intensities, and then you might make a comparison in your observation space. But you could also try to get directly maybe ice concentration and assimilate that, in which case your H would be like a linear projection from your model. But that's sort of the concept of this operation observator. Wow, my mouth is the observation operator. Thank you. Okay. This is just a cartoon of sequential DA that you might do with a Kalman filter. This is different than 4D-VAR, but again, just to give a sense of how DA might work. You might have some initial state, an initial guess of your background error covariance. You'll predict that, so you'll vect it forward with your model. You might update your error covariance based on what you know about it. Q would be a specific matrix. It's hard to know these matrices in reality, but you might update that. Then you'll take that forecast and produce an analysis so that you have some best estimate of the analysis, which you'll update here. So here's like your Kalman gain, giving you your analysis. And then you'll forecast from that previous analysis. Well, sorry, then you'll get an analysis. This would be your best estimate of the state. Then you'll repeat. So you'll forecast, update things and compare, get your analysis, get another analysis. And you could sequentially do that in time if you were doing something with a Kalman filter. But that's roughly the idea. You're always forecasting and comparing to obs and forecasting and comparing to obs, cycling through. Okay, so that's a very quick, very brief overview of data assimilation. But let's talk about what JEDI is. And JEDI is a data assimilation system. So at its core, it stands for the Joint Effort for Data Assimilation Integration. It's a project funded by NASA, NOAA, the Air Force, the Navy, and the Met Office in the UK. And the idea is to build a common data assimilation system that each of these agencies who have different models, NOAA has GFS, NASA has GEOS, the Air Force is using MPAS, the Navy has Neptune as an ocean model, the Met Office has ELFRIC as an atmospheric model, and the model. There's lots of models, but they all use DA. They're all going to use DA when trying to make predictions. So instead of writing a separate DA system for each of these models, it would be nice if we had a generic DA system that they could all use. And this is really nice because then once you bring your own model, you can take advantage of all the algorithms that are already in JEDI. So if there's a new innovation in JEDI, it's immediately available to you, provided you've written an interface to interact with JEDI. So once you've done that work, anything that goes into JEDI is available to you, and all of these agencies are collaboratively working to improve that through funding the Joint Center, and also in their own places. We have people we call in-kinds who are also working on JEDI as well. And all of that collaborative effort hopefully gets to benefit everybody. Some of the things that are in there now, there's 2 toy models that you could play with now if you wanted to. There's an L95 and a QG, but GFS, GEOS, MPAS, ELFRIC from the Met Office, etc. JEDI itself is essentially a bunch of code repos. One of them is OOPS, the Object-Oriented Prediction System. This is where all the DA algorithms and the toy models live. We have UFO, which is the Unified Forward Operator. So this is a generic observation operator that any of these models can use and take advantage of if they want to go from, say, sea surface salinity to some microwave measurement in space. They don't all have to write one. SABRE, which is the System Agnostic Background Error Representation. These are those B matrices. We have IOTA, which is the Interface for Observation Data Access. This deals with different observation file formats so that everybody can take advantage of all the OBS that are out there. VADER, if you notice the pattern at this point, the Variable Derivation Repository. This is for variable changes between analysis variables and model variables, etc. And then CRTM, which is the Community Radiative Transfer Model, which is another observation operator dealing with radiative transfer. So this could be like CIC emissivity to microwave measurements at the top of the atmosphere. And those are definitely particularly chosen to be Star Wars names. There's a lot of those. But essentially, JEDI is meant to focus efforts in such a way that innovation is shared, accelerated, and is not reproduced. We don't want to waste money and time reproducing innovations. We just want to go forward and improve our ability to predict the weather. And then this is just an AI-generated image that I typed in, a JEDI working on data assimilation. And I guess it at least put a hurricane in the background there, but these things are always kind of fun to look at. Okay, So with that overview of JEDI, I now want to talk about a recent advancement that's gone into JEDI, and I think is a good example of why JEDI is a good thing. And that's this hybrid tangent linear model, which is aimed to be used with 4D VAR. So this is the 4D VAR cost function. What we're looking for typically with 4D VAR is an initial condition. So this is this X naught. We want to find an optimal initial condition. And really, I should say such that when we reforecast from that initial condition, the forecast that we get is consistent with the time series of observations that we have available. So here we've got our initial condition with our background and added into the cost function background error covariance, but then we also have this time series where we're looking at this M is the model going forward. So we're moving that initial condition forward, but is it consistent with each of the time series observations as we move the model forward in time? So we minimize this typically with respect to the initial condition. That's a simplified version of it. This is the general idea for those of you that haven't thought a lot about 4D VAR, but the idea is we make some first guess forecast, and then in our DA window from T0 to Tn, we have some set of observations available, and we minimize that 4D VAR cost function to find a new initial condition, say star, such that when we reforecast, we're much more consistent with those observations in our window. And we'll forecast beyond that, and we'll say that this is now our best guess of the near future. So before it would have been this dotted line, and now we're saying, oh, it's probably this, because at least in our window, this was consistent after forecasting from the new initial condition with those observations. There are different flavors of this. You can do parameter estimation, versions of 4D VAR, but at its heart, this is really what it is. So if we want to do 4D VAR, we need to minimize that cost function. So typically in variational schemes, we take a gradient and we try to find out where it's zero. So in this case, this is difficult to just do something like a finite difference. There are millions and millions of points in these models. That's not going to be computationally efficient. But you can formulate this in such a way that you do get a efficient enough algorithm to do this. And that's using this idea of a tangent linear model. So we introduce this tangent linear model, the TLM, where we linearize around the nonlinear trajectory of our model from sometime Ti-1 to Ti. So it's basically a Taylor series. We take our state maybe at Ti with some perturbation. We take M, which is our model moving it forward in time, and we say that plus the perturbation is like moving the state plus then the linear part with the small perturbation and then some higher order terms. This TLM allows us to write down the gradient in such a way that this becomes calculable. And this, I'll just say, is the most important part. This is where we'll use the hybrid tangent linear model piece, really this L here. You could think of it as like a matrix times this perturbation if you want. But that's what we'll be interested in. So just a note on how these models work. So typically they're sort of separated into model dynamics and model physics. The dynamics are the things like relationships between pressure and temperature, sort of that we might be able to write down Navier-Stokesy type equations about. Those are the sort of the simple things where the atmosphere moves from high pressure to low pressure. And then there's the model physics. So these are the processes that occur on spatial scales that might be smaller than a grid box or just really complex like cloud formation, or is it going to rain? What are the aerosols up to? What is the chemistry of the atmosphere doing? Those are all the physics parameterizations. Typically, the way these models go is we advect the atmosphere with dynamics. We solve a physics problem with that new advected atmosphere. That informs the dynamics if in whatever ways it should. And we repeat, we advect, do physics, advect, do physics in that kind of cycle. So for the tangent linear model, the way that works is very similarly applied, if we're going forward in time with the tangent linear, we apply the linear dynamics forward, and then we apply the linearized physics. So it's still a two-step process. The dynamics of the tangent linear model are the easy part. That's typically more straightforward to implement. There are programs that can do that automatically for you, almost. But the physics part is hard. There's a lot of if statements and other things that go into those, and taking derivatives of that is difficult. And it can be really, really time intensive, lots of full-time employees to write a tangent linear model for a complex model like that. But you would need it to do 4D VAR, which arguably produces some of the best forecasts. Then there's what we call the adjoint, which is just the adjoint of the tangent linear. The way that one's advected, you sort of undo the linearized physics, and then you apply the linearized dynamics backwards. Once you have the TLM, the adjoint's not too hard to code up. There's sort of formulas for doing that. You think of it as, in terms of those matrices, it is just the adjoint. If you think of the tangent linear as an actual matrix, it is just the adjoint of that matrix, just the transpose. But it gets a little more complicated when things are algorithmic and there's if statements, but getting the TLM is the hard part. And then it does take time to do an adjoint as well. But getting all that physics in the TLM is really the difficult part. And that's where we want a better way to do that, if we can, so that models can improve at a faster rate. So just a summary of how you might do 4D VAR. So first, you'll integrate your nonlinear model, your full nonlinear model forward. You'll save the trajectory in your assimilation window. You'll look at these weighted observation increments. So here you're comparing your model here to the observations. You'll want these often called departures. We'll use the adjoint, which when applied to a vector sort of goes from ti to ti minus 1. You can think of it that way. But we calculate the gradient in the following way. So here's the gradient of that cost function. If you look at these L's, remember L was the tangent linear model. These L transposes are the adjoint. So we get the gradient really from the adjoint acting on all of these departures of the model and observations at each of these times to give us the gradient. And then we can do conjugate gradient or whatever to minimize this. And then eventually we get a new initial condition, and we might actually integrate from that again, and we'll repeat this process until we get some form of convergence. So main points, it's the tangent linear model and adjoint that make 4D VAR practical. To reiterate, if the model physics change or added or updated, they won't be included in the TLM right away. It can be very difficult to update them. This is where the hybrid tangent linear, or HTLM, comes in. It's going to use an ensemble of nonlinear model runs to correct an incomplete TLM. And then from that, you can also get other benefits for scientific applications. So you might be a modeler and you add a new model component or a different physics parameterization, and you want to test that with 4D VAR because you might want to, I don't know, look at a volcanic event and the aerosols, and that might not be in the TLM. You could use the hybrid tangent linear model to do a reanalysis of that, or test 4D VAR with a new physics parameterization, right? It gives you the ability to do things a little bit quicker and with less work. So let me just talk about how it's implemented. And the starting point for that is this localized ensemble TLM, which is not a full HTLM, but the basis of it. So if you recall, the TLM advances an increment from one time to the next. Just L times some perturbation of the model at a previous time gives us the perturbation at the new time. So instead of calculating this L, we might just try to learn it. Just do a linear regression and learn this thing. So we'll consider the jth element of this state vector, which is a list of the pressure and temperature and everything at every point, and a perturbation of that. And then we'll suppose that it depends on a bunch of points around it. Think of that as your stencil, for example, if you're writing a numerical solver. So here's an illustration of that. Maybe we want to update at this point, and we say, this is going to depend on a whole bunch of points around that. And we'll call that the influence region for that point. And then we might try to learn the rows of L by saying, okay, my perturbation at time ti will be, say, the jth, for point j, would be the jth row of L times this influence, times that influence region, right? So here, S is the number of influence region. In this case, you could think of it as like a sphere around the point. Everything that it depends on could be a lot of points, but it'd be this times its stencil, so to speak. And then that should give me the updated point. Now, I don't know what that is, but I could then take an ensemble. So I've run a nonlinear ensemble, and I actually, in this case, know what the perturbations are at each time because I've run them through the whole window. So I would know the left-hand side here, and I would also know the right-hand side, and I could sample the influence region points along that right-hand side. and then set up an equation to solve for this row of L, right, using the ensemble. So in a compact form, that looks like this. And all that is a least squares problem. So we take the normal equations, multiply both sides, by a transpose, and then we can take a pseudo inverse to get a best estimate for this mu j transpose term here. So if you do that and you play that game, you can build an approximation of your tangent linear model by finding each of those, right? And then you'll have some matrix, and then once you have that, take the transpose and you've got the adjoint and you're good to go. The problem is if you do it purely this way, you need a big sample size around the points, and you need a large ensemble size. The bigger those get, the more this approaches the tangent linear. That was proven. So it's a good method, but computationally speaking, it's impractical for these large scale models that we use to predict the weather. So this is where this idea of a hybrid tangent linear model comes in. And this concept was developed by Tim Payne, who's at the Met Office. There's a paper published in 2021 that you can look at if you're interested. I think it's pretty well written. But the idea is that instead of directly trying to get the entire tangent linear, what we're going to do is use whatever tangent linear model we have, even if it's missing physics, or maybe it's only the dynamics, which is the easy part to code. And we're going to use that first to move our ensemble a little bit in the direction that it should have moved. And then the idea is we should be able to have a smaller ensemble and a lower sample size to then calculate a correction to that. So the idea is if we have what we call a simplified TLM, which might be, like I said, just missing physics or dynamics only. Whoops, there we go. Call it M. That might affect our perturbation from I-1 to I, but it's not quite correct. So we put this little minus. That's our best guess of what should have happened. But then what we'll do is use an ensemble of nonlinear runs to find a correction to that. So we can apply to the Ti minus here, this N, to give us hopefully what it should have been had we coded the entire tangent linear perfectly. Right, so we use our incomplete TLM, and then we find a correction term instead. And the benefit that that gets us is that we need a smaller ensemble size, but most importantly, we don't need a really big influence region. We really just have to sample above and below the point on the column, which also makes it a parallelizable problem, and that's important as well. But so instead of sampling points horizontally and up and down and everywhere, we're just looking at points for whatever point we want to update, just above and below it. Even as low as like 2 points above and 2 points below seems to actually produce pretty good results. So let's talk about how this works in practice, but well, here's the equations, I should say. So we would have, these minuses, we would have advected our ensemble bits with the incomplete simplified tangent linear, and that's the ensemble we take, but it's otherwise the exact same equation as before. Let me show you what that matrix looks like, because it's nice to have a visualization of that. So this matrix here, since we're just sampling on the column, the idea might be like, let's say I have one ensemble member here. I'm looking at one ensemble member, and let's say it has two variables, and I want to update this grid point. So this is the same point in space, right? Purple is one variable, call it pressure. Blue is temperature. The way we'd organize this matrix, if we took an influence region size of 3, so I would take a point above and itself and below, that's 3 points. I'd put that in for one of the variables, and then for the other variable, take a point above, itself, and below, and I'd put that also in the matrix for one ensemble member. This might be another ensemble member and another ensemble member. You don't have to use every variable of the model, but it depends maybe on what you're doing, which ones you could choose. You can choose which ones you want to update, but typically you don't just put one variable. You've got all of these variables interacting with each other, but in this case, just on the column. So that's roughly what this matrix here would look like visualized. Hopefully that's helpful. So here's the general idea. I like cartoons, so let me show you roughly how this is. The idea is that, we have our simplified tangent linear, if we had our perfect tangent linear, that would be the green one. And we move that in time. This is telling us where these perturbations would go, right? But we may have an incomplete TLM that's missing some physics, so it's going to be off a bit. But then we're going to apply an HTLM update. That would be this blue here. So that hopefully would push us in the right direction. We might go from there, push us in the right direction, go from there, push us in the right direction, go from there, push us in the right direction. So we're adding these corrective steps since we're missing things in the TLM. How do we calculate the coefficients? Well, the idea is we have some nonlinear run. This might be the nonlinear run that we would actually use in 4D-var itself if we had a tangent linear. But what we'll also do is run an ensemble around that. So we run a nonlinear ensemble. We'll initialize increments, so little perturbations between all of those ensemble members and the run that we would do the 4D-var with. So those are over here on the T0 axis showing up. And we'll also do that at every time that we would have had observations in 4D-var. We'll initialize these increments, differences between that center one and the ensemble. Okay, so we've got these nonlinear increments. We're going to save those. Then we're going to take the ones that were at the beginning, and we'll move those forward in time with our simplified tangent linear model. So it's missing physics, but if it were perfect, it would have moved these to where they should have gone, but it's going to move them forward in time to somewhere. And we're going to say those are now, these dotted increments are now our best guess. Those are our dx minuses. And then we're going to remember that we had the actual nonlinear increments, which is where the TLM should have put them. And we're going to compare those to what the simplified tangent linear said. And we organize those then into the equation we solve for this Vj, which will be the rows of that update n, so that we can then update those. And in reality, remember, I was showing in that cartoon, we have multiple variables, right? So in this would be for one grid point and one variable at each of these ensembles. Over here, that S is the influence region, which would be points above and below, but also for various variables. So this might be for one variable, another variable, and another variable. But then we just solve a least squares problem from that. So the way that it's implemented is using this alternative form for the update. Instead of multiplying n, we actually just multiply n and then add it to the original increment. So it's a slightly different n, but the idea is the same. We're going to update it. The reason we do that is because we can break it down into a grid point by grid point update, which is easy to apply in for loops in code, where we're doing this C, which is what we call the HTLM coefficient for a grid point at J, which will multiply the influence region for that grid point, then get, which this is a dot product, and then get added to that grid point to give us our update for that grid point. And C is calculated in terms of those matrices here, where lambda is just some kind of regularization that we apply. The bigger lambda is, the less update there is. And this delta E is the difference between that grid point of the nonlinear and then what the TLM said it should have been at that time. If you want to put it into a matrix form, you can. So in the idea is that in combination with this simplified tangent linear, we'll move an increment from one time to the next in 2 steps. We'd apply our simplified tangent linear, then we apply our update, and we'd have everything updated. For the adjoint, we would apply the adjoint. So I'm taking a transpose here of this guy to the previously updated one to go back, and then the adjoint of the tangent linear, so to go back. That's the idea. So that's how we would calculate the coefficients. The way we would do 4D-var is to calculate those coefficients first. So before we do a 4D-var, we calculate each of those Cs. So just to remind you of the sequence, we run the ensemble, save those increments, advect those increments, and then compare those increments, and then calculate each of those coefficients. In between, I should say one thing that's done is if I go from one time step to the next and I calculate coefficients, say here, I will apply those to update before I move forward again to get the next set of updates. So we also try to stay close to what the TLM should have been doing as we calculate coefficients. But you repeat 3 and 4 until you're all the way to the end of the window. And then after that, you have coefficients for each time that you were going to apply a tangent linear or an adjoint, but so that you can provide those updates as needed. And then if you've trained them on a lot, they may be reusable. Or if you just do, if you're going into a second outer loop, things may not have moved that much. You might be able to reuse those instead of have to recalculate them too often. Okay, so that's the general idea. I'll show you some results of how it's working in a minute. But let me just share sort of how this is implemented in JEDI. And I won't spend too much time on this, but this is one of the nice things about JEDI is this is very generally implemented. We have a class called, everything's in C++, hybrid linear model.h. This constructs the things you need, like the simplified tangent linear model, the hybrid linear model coefficients class, which handles moving the ensemble, calling the calculator class to calculate coefficients, storing the coefficients, doing all of the busy work that goes into it to make it run well. The HTLM calculator class does all the math. There's a regularization class to do different kinds of regularization, something to deal with the ensemble, different versions of simplified tangent linear models that have multi-resolution and residual formulations, and they can all be swapped out and replaced with each other to fit what you need to do. So like if you wanted a different calculator class, you could use it. All of these ideas it's meant to be very general, but this is more computer science stuff, so I won't spend too much time on it. But let me show you some of the results just very quickly. So I should say, so for some of these figures I'll show, the simplified tangent linear we're using is called FV3TLM. It's in our FV3 JEDI repo. It has no physics. It's just dynamics, no atmospheric chemistry. But we used it with GEOS. So this is NASA's model. So we have a GEOS ensemble that has physics and is advecting chemistry, et cetera. And we see some nice reduction in linearization error when using the HTLM versus not. So I'll just show that. So this is more dealing with atmospheric chemistry, which would not be in the TLM, but you can see this is the linearization error over time. So if I'm just using FV3TLM only, that's this blue line. Error increases in time. That makes sense typically with linear approximations. And then all of these lines down here, all of these are using the HTLM. So it's pretty much driven to 0. The ensemble sizes were not that large. I think here 15, 20, 25, 30, they're all kind of on the 0. Influence region size here was 9. I think that seemed optimal in this case, but honestly not that big, and getting a good reduction in linearization error. They're all sort of squashed to 0 compared to this. If we zoom in on that, here's the different ensemble numbers for influence region size 9. There's like a spike up here, but we're still on the order of 10 to the minus 13. That's working really well. This figure here shows that for variables that we don't directly update, because we might not include all of those variables in that matrix, so even if we don't directly update them, we still get some benefit. So this is for air pressure thickness, one of the variables. This is without using the hybrid tangent linear model, but we get not a flatten out to 0, but we do get some reduction in linearization error, even for that variable that we weren't directly sampling and updating, which is really cool. So that's very exciting. And I should say about this is with GEOS. Recently, our SOCA team, which is ocean and sea ice, they've started using it. They don't have a tangent linear, so they're using an identity model for that, but they're seeing good reductions in linearization error. This really should be able to run with any model with a JEDI interface, which is kind of exciting to see so many people start to use it, because it's a new innovation and it's ready to test right as it goes in, which I think is cool. And I think highlights what makes JEDI special. So that said, let me just talk a little bit briefly about JEDI in general and how you as mathematicians or whoever else might watch or see this might be interested. So maybe you're just into algorithms and data assimilation. So if you are, and you have ideas about DA, interesting particle filter ideas or ensemble Kalman filter ideas or whatever, you can develop that code in JEDI. And you could start with toy models. There's Lorenz 95 and a quasi-geostrophic model in the OOPS repository. OOPS usually builds pretty easily. You could start implementing your algorithm and testing it with those and getting results. There are plotting tools available to look at that. And the nice thing is if you've done that, for example, Peter Jan was here visiting for a while, and he and a grad student implemented a particle filter and tested it with L95, and it is now in JEDI. It has some restrictions. We can't really use it with the big models yet. That would take a little more development, but it's there and it's available. So if you're interested in something like R2O, if you're putting this into JEDI, you can submit pull requests and we can look at these and you can demonstrate that they work. And this can keep it from just sitting in a paper for too long. If it's something that's useful, it can get out there and actually get applied. So I like that a lot. it could just be that you have an algorithm that you want to test with an atmospheric model. Those things it is hard to run MPAS or SICE or GFS on your own. But if you install JEDI, these things are typically available for you to run it, especially if you use what we call a pseudo model, which makes it a little easier just reading in states. But maybe you just want to test an algorithm you have with a larger model. JEDI is a great place to do that. Gives you access to those things. Maybe you're into AI. So there's lots of places where AI fits into DA, and we want those things in JEDI. Please add those. Please add those and test those. Maybe you have new observations and you want to test their impact on analysis. JEDI will give you the DA. You can just bring the OBS and Yoda can convert them for you. If you're on the modeling side, you could test model physics and let JEDI do the DA parts. You might want to compare a reduced order model to big ones. So you can use JEDI to get data from large models after doing a 4D VAR or something. Parameter estimation, more AI. We'd love for if you have some AI algorithm and you want to benchmark it against something standard like 3D VAR or 4D VAR, you could have JEDI handle that for you to compare to your other thing. Or if you like observation operators, those are often in model parts. You love radiative transfer. Maybe you want to contribute to the community radiative transfer model. Lots of things you can do. For climate, DA is useful for climate studies. So I showed it before, reanalysis data, that fills in the gaps. So these are, we take the big numerical models, NASA produces the MERA product, ECMWF, ERA5 data, but it's filling in what's been going on over, the last 50 years that we have a satellite record and enough data. Gives you a lot of tools if you're interested in developing new reduced order models to study a specific climate process or something. These can be really informative. So there's a record to use. But I'd also argue that extreme weather prediction is more important than ever. We're starting to see more and more extreme weather. I think everybody's noticed it. And that's a part of dealing with climate at this point. And I think there's a lot that mathematicians can bring to the table to help improve that extreme weather prediction to save lives. So that said, a couple innovations that come to mind for me for JEDI that I'm really interested in. I would love to generate background error covariances or initial conditions with AI. So this picture right here was a prompt I sent to Google Gemini to generate an image of a storm system over a weather map of the Midwest US. And it kind of looks realistic. I mean, I'm sure it's not, but the idea is that these diffusion models, if trained on the right things, can really produce things that are statistically consistent with whatever they're trained on. And that would be really useful to generate, say, a rapid ensemble to estimate error covariances, or generate an ensemble to run for the HTLM to get a statistically consistent ensemble in a quick way. That one's kind of exciting. There's lots of AI stuff that could be done, super obbing, faster physics parameterizations, lots of places where that goes. And AI and DA are intimately related anyway. But then also, I'm interested in reduced order models myself, and I would love to see a generic reduced order model suite in JEDI that provides parameter estimation. These are figures from some work that I did with Julie Sherman, who's a grad student at Utah, and Emmanuel, who introduced me today, and Chris Jones and Penny Wu from ASU, where we looked at a simplified model, the Rosmeikin model of the stratosphere, the polar jet, but assimilated ERA5 data, so this reanalysis data, to estimate these two driving parameters, lambda of t, which here is blue, and h of t in the red. H is like perturbations coming from mountains into the jet stream, causes Rossby waves. Lambda of t is related to the thermal gradient that really sets up the polar vortex itself. And we were sort of interested in what does it take to get that reduced order model to look like the real big, full reanalysis data set, with all the physics and everything included. We found that we could get it to by making these parameters time dependent, lambda and h. And what was really cool is this blue is the state space for mean zonal wind here and lambda, and these orange lines are the equilibrium solutions for the autonomous version of the system. And this thing's kind of hovering right around it as we go through the seasons, which is really neat. It shows that the reduced order model was basically capturing the important physics, I'd say. And we also found out interesting things around sudden stratospheric warming events by being able to assimilate that data. And I'd love to see something in JEDI where you could prototype your equations It sets it up so that it can be run on HPC, and then maybe you can do an ensemble data assimilation, like an ensemble smoother or something to get parameters. It'd be a lot of coding, but it would be interesting, and I think a fun project as well. But I think that's another place where DA comes in, is understanding these models. So let's see. So maybe I'll just wrap up with a little more on JEDI. So if you're interested in JEDI, you want to learn more about it, how would you get started? So it's written in C++. There's also some Fortran around. It is definitely an object-oriented thing. We have a lot of templated classes. They're templated on the model. So might be GEOS or QG or L95 or GFS. There's classes like increment.h that represents an increment, state represents a generic state, an ob space, a generic observation space. Those things are great for JEDI being generic, but it does introduce a learning curve if you're not super familiar with object-oriented programming, and it can take a little bit to get going. JCSDA used to do these JEDI academies, which I think were helpful getting people started. Right now, we're not doing that. We're more focused on getting JEDI operational for NOAA in the Met Office at the moment, but I think we'll be coming back to this. I'm sure we'll be discussing it this week at our relaunch event that we're doing this week. But there are old academies that you could look at on our JCSDA YouTube channel. There's also documentation, Joint Center for Satellite Data Assimilation, JEDI docs, read the docs hosted. Sorry for the long, but if you Google JCSDA, read the docs, this will show up. Just make sure it says latest. But word of caution, JEDI moves very fast. New things are coming in all the time. The docs aren't always up to date, but we're working on that. But if you do get going, it's worth it. You can do a lot, you get a lot of things for free, and then your contributions can be immediately put into a place where people that would use them for real application would see them. And so I did put this picture of an angry cat on a computer because sometimes it can be a little bit frustrating to get going. But once you get going, it's not so bad. So just one last thing that I wanted to mention. When using a complicated system like JEDI, it's nice to have a workflow that makes things easy. So we have an in-house workflow that we call Skylab. It's essentially full of generic and some specific model configuration file templates, and also what we call experiment YAMLs that define an experiment to be run. It depends on EWOC, so more Star Wars, but experiments and workflows orchestration kit. This generates config files, run scripts, et cetera, that you might need to run on HPC. We have R2D2, which is the research repository for data and diagnostics. This is just a database of model states, increments, analyses, observations, experiment results, et cetera, but just a MySQL database that holds all the things you need to run models. SimObs is full of plotting scripts to evaluate results, et cetera. And Solo is not an acronym, but just standalone Python tools that we use in some of the other repositories. That's generally what makes up Skylab, but it's a workflow suite that helps us do our work when we've put something into JEDI and we want to test it. So for us, it's our test bed for development and gives us a way to reproduce experiments exactly. We can rebuild from the same settings on the same system, et cetera. It's also our demonstrator of new capabilities. It's what we use to show our partners what's been done, and we put the cutting edge into that workflow as soon as we've developed it. It goes into Skylab as fast as we can get it in there. At the moment, it's not public. So if you have access to JCSDA internal, you could play with it. If not, right now it's not public. That's for a couple reasons. We can't offer support to new users. There's not any money earmarked for it. So that might frustrate people. And then R2D2, it's on a set of HPCs that we have, also in the cloud, Amazon buckets, et cetera. But those polls cost money, and we have to figure out a way for any user to have something like R2D2. There is a local version that you can install. You just wouldn't have all the data available, but you could set up your own, and there's discussions about how to make that work. And we will be actually discussing this at our relaunch week this week. I think I was talking to Unique Tremolay about this last week, and we really want to figure out a way to get this usable by the public so that more people can have access to the workflow, the data, and get testing and developing and contributing to JEDI. So just wanted to mention Skylab there. There's a YouTube video about Skylab on the YouTube channel if you're interested, with a demo, sort of how it works, what it's meant to be. There's more information on this website here where we show our releases. What can Skylab do now? You could train a static bee. There's a suite to do that. You can run experiments with hybrid or ensemble bees. You can run the HTLM with 4D VAR. There's 3D VAR, 3D FGAT, 4D VAR experiments for various models, aerosol experiments for geos. You get metrics like forecast scores, OBS impact, the usual suspects. We're working on continuous DA for NOAA, which is being able to add observations between outer loops, as well as shifting the assimilation window between outer loops aimed at fire weather. A lot of this is in JEDI right now, but we'll be putting it into the workflow. And then you can check out some of the, showcase experiments at skylab.jcsda.org. If you're interested, I can show you quickly what's there, and then I'll just wrap up. But if you click on this, here's Skylab Aero Weather 8. That's one of the experiments. You can look at various diagnostics, OBS diagnostics. You can look at, say, computational cost. You could look at cost function convergence. Elapsed time. There's a whole bunch of stuff. Look at the analysis itself. All of these things get spit out when you run a Skylab experiment so that you can evaluate things, different window lengths, etc. But you can explore that if you're interested. And let's see, I think with that, just to very quickly summarize, DA is needed for accurate weather prediction. JEDI is collaborative, open source to a point. There's internal and public, but whatever's internal goes to public eventually. The HTLM is a recent advancement, and there's a lot of typos there, but it's already being used with multiple models, atmosphere, ocean, chemistry, which is really cool to see. It's working well. I think I like that this went in and is being used. Anybody in principle can contribute. JEDI is meant to be used operationally, so if you're contributing, people will use it and may use what you contribute. There's a bit of a learning curve, but it is surmountable. And with that, I'll just say thanks. And if you're interested in playing with JEDI, there's the GitHub repo. And if you have questions, please feel free to email me and I'll see what I can do, hopefully to get you going if you get stuck. So thanks.
All right. Thank you, Christian, for this wonderful talk. All right. Thanks, Christian. Okay, now at this time, are there any questions for Christian? Okay, so Colin has a question. Go ahead.
Yeah, I guess well, I probably have a few questions. I guess the first thing that I wanted to check in on is you mentioned that there's some limitations currently in terms of R2D2 has kind of hooks into like internal usage with like AWS, things like this. As a outside user, let's say at SIO, where a lot of us, we want to use JEDI, probably, use Skylab as it becomes available and accessible to us. Could we, I guess, configure R2D2 to gather data from sources that we typically utilize, like the NOAA, GEFS, AWS public bucket, things like the NCAR Research Data Archive, where we typically gather like global model data, observations, things like this that are just public through like Globus or AWS free?
I believe the answer to that is yes. Eric Lingefelt is in charge of R2D2. He would know the most about it. What I can say is that so for example, I run R2D2 on my laptop, but I'm not accessing any NOAA buckets or anything. There's a local version you can create, and you can put whatever data into that you want. So if you pulled it and put it in there, it should be available in R2D2, your version of it, on whatever system you're running. So I think you could certainly do that.
Okay.
But I believe the goal is to be able to make it more configurable, but I don't want to quote exactly on that. I'll probably learn more this week. It's one of the things I've used, but Eric would be the person to say exactly how you could connect it to other things. But at its heart, it's a MySQL database.
Okay. Yeah. So at the end, like there's probably some way to get it just to work with what would be our typical data sources.
Right. I think so. And worst case, it might be you write a script to pull it and place it in R2D2, and then it's available in R2D2
Okay,
to pull
sure,
from
sure.
Skylab. But like all of our workflow would call from R2D2 to grab something or store something or etc. Yeah.
Okay, cool, cool. I guess the next question I wanted to ask is, what is, I guess, the current I don't know, level of support and integration of MPass specifically within Skylab?
So we run MPass experiments. There's some 3D VAR. There's no 4D VAR because we don't have a TLM. I'm intending to try it with an identity TLM and the HTLM for fun. Well, and also testing.
Yeah, yeah, cool.
There are, I can say this, there's a series of experiments in there that run and work. So there's workflow for MPass. New things I think that are going in, I believe we're working on getting our B matrix training suite to work with MPass.
Cool, cool, nice.
I know BJ is interested in this at M-Cubed, and but I imagine there's going to be a lot more. One of the things this year that we're working on, because NOAA will be using, I think, MPass for regional modeling soon.
Right.
A lot of our development is now focused there, and we'll use Skylab to demonstrate the things that they want. So probably will get a fair bit more attention than it has, but there is definitely workflow there.
One actually specific question. So you mentioned that so the 3D methods are supported. Does Skylab support EDA, the 3D
Yes.
formulation? Cool, nice.
Yeah, there's some EDA. We've done that with GFS. Clementine Gas is working on EDA with GEOS, but also we're trying to, right now we can't run GEOS, what we'd say in core, which is JEDI calls the forecast of GEOS. But there's a lot of progress on getting that going to where everything would be just handled by JEDI, which is the ultimate goal. We can run MPass from JEDI, well, at least with MPass JEDI. But yes, there are EDA experiments that have been done. I think if previous Skylab experiments on skylab.jcsda.org, I think some of those are EDA. But yes, short answer, yes.
Cool. And if I can ask one last thing, I was just curious if the diagnostics, let's say forecast quality, let's say obs versus background, or I mean, first guess or analysis, something like this. These sorts of diagnostics, does this include like the integration of model evaluation tools like is going into UFS, or what does that look like?
We're slightly integrated with like Met Plus at the moment. If you're thinking of that, but then I think our eventual goal is to use Google Weather Bench for a lot of these.
Oh, okay. Okay,
So
interesting.
that's something that Sam Matika has been working on implementing. Right now we have some in-house stuff that we've written, but the goal is, I think, to move most of that to Google Weather Bench is what we're most interested in.
Okay, cool, cool. All right, yeah, thanks for all the questions.
Yeah, of course.
Someone else in the audience has another question?
Yes, hello. So I'm Hans Engler. First, a shout out to JCSDA. 10 years ago, I spent a very productive semester as a guest scientist at the NOAA division, the relevant NOAA division that's working with them mostly on the microwave data assimilation. My concrete question here is this, it may be nonsense, but so the examples you gave have to do with continent-wide or fairly large weather prediction. Are there any applications of these methods in smaller scales, mesoscale, at the 100 or 100 meter, 1 kilometer scale, as particular to predict extreme weather like tornadoes and things like that? Does it make sense, or is it maybe happening too fast to use data assimilation methods?
So yeah, for something like the hybrid tangent linear model, it is computationally intensive, which does slow things down. I would say in its present form, if you were trying to predict tornadoes in the next couple hours, it might not be all that practical because you'd have to initialize your ensemble, run it, calculate coefficients, do the 4D VAR, right? I'm sure it would improve things, but if it's a timely thing. Maybe for something like a longer term hurricane track, which is a larger scale, I think that could be useful. But I should also say at the moment, it's not running on a GPU at all. It's just being parallelized, but it is so parallelizable. I think if we were to, and there's an effort here to get more things in JEDI running on GPUs. I can't say because I've not tested it, but if calculating the coefficients is maybe the most computationally expensive thing, and you're doing this column by column, but you can really distribute that on a GPU, that might speed things up to make it a little bit more feasible. Also, if you have some very quick to run AI ensemble, right? So you've got an emulator, that might work. But at that point, maybe you've just trained something to correct a TLM at that point anyway. So I'm not sure. Yeah. So yeah, I think for something that quick, maybe not as useful, but something where you have, a few days to look at, like a hurricane track, I think it could be.
All right, thank you.
Mhm.
All right, Christian, a very quick question before you leave. So this object-oriented prediction system, oops, this is accessible to this GitHub link that you just posted.
Yeah, you would do github.com/JCSDA/oops.
Gotcha.
And then if you want to try it out, which you certainly can, go to the documents, and I would maybe as a first try get the Docker container. You would have all the code libraries that you need. That might be the easiest way to do it. Or you can look at installing SpackStack. That takes about half a day and is probably the best thing to do, but the container in principle should work. And then you just download the container through Docker and you would run that.
Okay, sounds good. But now I'll let you know if I have any questions. Okay, so let's thank Christian one more time for this wonderful talk. Okay, so at this time, thank you again, guys. So we'll end the talk right now. Thank you again.
All right, thanks, everyone.